Okay, let me start. Okay, just put it on. Okay, I just remind you that what we spoke it on the previous lecture, and actually we considered the initial equation here. They briefly written here, all of them. This equation includes continuity equation, then equation for the gravity, because actually the heating up of the gravity, heating up of some particle result in the diminution of density, and it's going up. Okay. Just for the moment here. Okay. Okay, it's good. Yeah. Thank you. Of the Archimedean forces working via gravity, so we need the gravity equation for gravity potential. Then the next we need the equation of state, and also we need energy equation, which better to write down in entropy term, and the final equation, but perhaps the most important one is Navier-Stokes equation. We consider it in detail, and this machine is working in such a way that we have liquid core of the planet, or in some planets it's not core, it's maybe some metallic hydrogen, like in Jupiter, and it could be another substance. But even there is icy planets like Neptune and Uranus. Here we have icy stuff which becomes under this huge pressure near the center of the planet very strong, so it's become metallized, and it has some conductivity as well. Everything is working on conductivity in terms of creating the magnetic field, which we can examine straight out. In fact, there is also some contribution of the convection. If no convection exists, then there is no dynamo as well exist. Moreover, it could be a situation when the convection exists, but there is no dynamo, which perhaps occurs in the modern Mars, in the Venus, and so on, because definitely there is some convection there, but it's not so strong to support the magnetic field. So the subject for studying the convection itself was to be pushed out. And so I just show you all the equations. Then we use, first of all, we are of course related to the Earth. And for the Earth, we just estimated different values. And using this value, we can estimate different terms in these equations, which I showed you previously. And it's important conclusion that first of all, as thermodynamic variable, we should explore the pressure and entropy, or more precisely not the pressure entropy itself, which is here noted by the capital letters, but the deviation from the adiabatic pressure and correspondingly from adiabatic entropy. And also there is also deviation from the adiabatic gravity potential. So all these three most important components, together of course with velocity, they constitute the convection system. And but we effectively remove temperature from the system. But nevertheless, we use that there is small deviation of the temperature from adiabatic state, which this adiabatic state marked everywhere by the subscript A. And so we then expand the deviation of the temperature in terms of the superadiabatic pressure and superadiabatic entropy. Anyhow, this okay, I will just say pressure and entropy, not saying that it's superadiabatic, that is some addition on top of adiabatic value, because finally we investigate them, so why not to repeat all the same. So P small and C small, and I will simply called pressure and entropy, while of course it's the deviation. And it also can be expressed directly in the measurable things. There is adiabatic temperature, very well known for the Earth, and from the seismic data there is CP, also very well known. And also there is the expansion coefficient. Unfortunately, it's not so very well known, but order of magnitude with accuracy of about 10%, 10 or 20%, we can explore it. And again, there is also adiabatic density, and in the similar relation, we can also relate the density, and it's also very well known again. And this is representation. So, it's interesting to know that there is also very valuable term in all this equation, which I will show you later. And this is actually constitute that the adiabatic entropy is not dependent on any special coordinate. It depends only on time. So the gradient of adiabatic entropy is dependent only on time. And what represents this dependence of time? We put it like S over dot. So it's more simple stuff, and it could be roughly estimated like the output heat flux which coming out from the planets, and then we divide it by mass of the liquid part of this deep interior of the planet, and of course also we multiply by some again TC here. This means that this reference on core. So in case of the Earth, this is this first will be the mass of the liquid core, and the TC here is an average temperature of the core. But of course, if we consider not the Earth and Earth-type planets, we will go not the liquid core, but also, for example, in Jupiter, we have metallized hydrogen on some depths. And so it's sort of the metallized hydrogen, which becomes the property of liquid, but still keeps some gaseous properties. But, and it's quite important that this relation constitutes the process of the cooling down of the planets. More precisely, not all planets, but only this liquid part, liquid, gaseous part, whatever part. The most important thing that it's conducting part. And so it can work on this process that simply just cooling down. And in the Earth, this process is not so effective, but it's very dramatically effective in Jupiter, for example. So in this sense, and finally, you can feel what is the entropy and why it's so useful. Actually, entropy is the ratio of the heat flux on the temperature. So this is how many temperature is required to rise the heat flux, for example. So we can, if we change some part of the entropy, we can change, for example, from the heat flux. If we rise, then the entropy is rise. If it's cooling down, like in present situation, then the heat flux is diminishing. And so everything is cooling down. And anyhow, we can very precisely estimate this term and work out how this cooling is working. So, and also there is adiabatic pressure and so on. So we can also further simplify all this equation, and eventually we arrive on the system, which is written like that. And in my previous lecture, I explained all these terms, so I hope that you all know all of them, and also the dependence from the adiabatic temperature takes this form actually, and all these parameters are very well known. And also you see that here we again have this S derivatives of S with time, and it's working like a cooling term. And also, of course, there is some heating term, and there is some term in all this the stuff which responsible for the viscosity. Oh, sorry, not viscosity, not viscosity, but diffusion, thermal diffusion. Here this term responsible for thermal diffusion, and it also has somehow sink nature, that it's just some heat is sinking in this place. And also we of course have boundary condition, and there are not only 6 boundary condition on velocity, there is also boundary condition on the entropy, which actually constitute that the gradient of the entropy on one boundary and another boundary is actually equal the difference between subadiabatic flow which is more than adiabatic, and adiabatic flow. And also just we need another one more boundary condition just to resolve the gravitational potential. Also there is some relation like I show you to you. And let's go to the final stage. We just now we make some sort of the conclusion and formulate all the equation which constitute this system, final one. Before that I was explaining in every detail how each term appears. Now I briefly proceed from all this term. And now let's draw the conclusion. Let's draw the conclusion. And this conclusion, in this conclusion, we just summarize all the equation and start from this equation. Oh, okay, from this equation, so in somewhat in reverse order. But we will keep the number of the corresponding equation as it was originally, just for you to understand. And actually, all this text will be available, so you can just see. Because there is also the processes that we return back to some equation to examine it, and so you can easily use this text to return and to understand. And perhaps, of course, we start from the entropy equation. So let's write down all the equation which is working in this system. We get the substantial derivatives of the entropy, and it is equal kinematic diffusion, which is usually turbulent diffusion, and of course the diffusional term, which is actually Laplace operator acting on S. Again, the small s, not the entropy itself, but just deviation from the adiabatic state. And also there is source, adiabatic source of the heat, adiabatic. I already show how it works, and it's divided by, and also quite well known, adiabatic density and adiabatic temperature. All these things could be changed. I mean, adiabatic temperature and adiabatic density, and as well adiabatic heat flux. And so these things could be changed, of course. And they change only with radius, because this is spherically symmetrical case. And we already spoke about that. I just remind you. And this is somewhat new formula which appear from the consideration that the influence of the pressure on this energy stuff and all this Archimedean stuff is actually negligible. But I'm not speak here in every detail of this statement, but it will be a separate chapter which is devoted exactly the verification how good is accuracy of this approximation. And so it can freely neglect by the pressure term and so on. So it will, separate chapter will be devoted by that, and also characteristic value we will estimate from the nonlinear term. So then the next equation, which also working here, is again very simple. It's just continuity equation, which is just because we neglect by the effects which are related with the sound of with the speed of sound, so we can completely neglect by substantial derivatives for the in the law of in the continuity law, sorry, in the continuity equation, we can completely neglect by the substantial variable, taking into account or not, taking not into account sound speed and sound effect, just filtering them out because we are not interested in them. And this takes a very simple form. It will be divergency of rho adiabatic times V. And it's constitutes formula 47B. And then neglecting, then as already was, again, I just mentioned that here we neglect by acoustic or actually acoustic changes in the density. So eventually we have this part. And also, again, we can refer that pressure is working. And let's now proceed to further equation. Now we take it from the previous part. And they are very important. And so we just proceed to the equation. Of course, the most important equation, Navier-Stokes equation. And this Navier-Stokes equation can be written in this respect in such a form, dV. Here, substantial derivatives is quite important, and we just estimate it. And it has two contributions of the viscosity. First contribution is just viscosity, which is related on the strain tensor, and it's better represented not via Laplace but double rotor, because it's when you are using double rotor, then you have a better understanding how this actually vector value is working, not the Laplacian, because if you use the scalar Laplacian, it will be not true. Actually, it's much more better to use double rotor in this equation. So, of course, here there is V. And then also there is the contribution, which is actually related that generally speaking, the velocity field is not exactly divergence free. So there is some contribution that it's at least in the Earth, of course, it's we can regard that it's almost divergence free, because the deviation of the density is just about 10% or even less than 10%. But if we consider the Jupiter again or Saturn, then we have very big variation in the density, so we cannot neglect the following term. And this following term is written like that. Here cos rho adiabatic, and then we have a gradient of the divergence. And then maybe perhaps the most important term in this equation, because if we are working in the rotation system, actually non-dimensional rotation system, we have Coriolis term, which is in dimensional units, can be written like that. Here we have unit vector in the direction of the axis of rotation, and then it's just multiplied it. There is a cross vector multiplier on the velocity. So here we end up with the Coriolis term, and it's interesting to mention that this, okay, This Coriolis term is first of all balanced. I slightly changed the order, which was in the original notation, just for your better understanding. But of course, it's the same. So there is also first things which work to balance the Coriolis flow. And this is first thing is not related to the velocity, but it's related to the pressure. More precisely to say, it's related to modified pressure. This modified pressure not only include the ratio of the pressure, or more precisely the deviation of the pressure from the adiabatic state divided by the corresponding density, but it is also include gravitational potential, or maybe more precisely, deviation of the gravitational potential of the gravity field. Okay, here we close, but we forget the main ingredient. What do you think? What is the main ingredient which is actually drive all this kitchen? What else we need? No, buoyancy force. Because actually buoyancy force, it has many names. It is buoyancy force, Archimedean, acceleration, and somebody name it. In this particular case, it's actually this buoyancy force or Archimedean acceleration is first of all, in the simplest way, of course, it's driven by the entropy. So it can be written, let's read it specially here. We just fit that quite successfully. And this entropy stuff, of course, first of all, it has entropy, or more precisely, the deviation of the entropy from a adiabatic state. It's fully dependent on the three coordinates of the space and time, of course. And then we have this combination of the expansion coefficient, adiabatic temperature, then Cp, and of course there is the gradient of the gravity, adiabatic gravity, which is just ordinary gravitational acceleration. On this boundary, it's about 10 meters per square second, about 10. So, we have the driving term, and let's keep the original number of this formula, 4.4a, just to collect everything in one place, all the system which are finalize this presentation. And then it's necessary to mention that there is also some addition to that. But if you can see on this equation, you have equation for the entropy, you have full equation for the velocity, you have equation for the not divergency free, but divergency of more precisely to say momentum, actually. Because it's not velocity, but multiplied by the density, it's sort of the momentum. Normalized momentum, if you like. You normalize it on the in this term. So actually, all this equation is already enough. If you just add the boundary condition to this equation, let's write them down. First of all, the boundary condition, which related to the energy, actually, to the entropy. Let's write it first. So we are adding boundary condition. Let's just state it. So there is actually a complete system which we can resolve. And it's important to mention that in this system, there is no need to resolve for gravitational potential, because it's very effectively collecting this effective pressure. And also we have very simple driving term. So now we can just state the boundary condition, and already on this stage we can solve the system. Of course, we are substituting proper boundary condition for our task. So let's start from the inner boundary. Inner boundary is denoted by I here. So we take the derivative of this entropy or deviation from the adiabatic entropy, and this is deviation from R, because actually the heat flow is preferably going in the radial direction. And at the first approximation, when you consider only adiabatic component, they depend only on radius. So it's quite straightforward just to define its radial derivatives of the entropy and express it in terms how many heat we put in the system or take from the system, whatever we do. So in this case, it working like that, minus TA. Oh, sorry, not TA. Here we should distinguish not only, so just for simplicity, we will not repeat here that this is adiabatic temperature. Of course, it's adiabatic, but precisely on the info. So we not build two term adiabatic and E just put here just I. So it will mean it will mean that this is adiabatic temperature directly on the inner core. And in the same way, we should write here. Oh, okay, maybe not enough space. Sorry. Okay, let's just state the boundary condition. It's important to mention that it's clear that it's equation, but now we proceed to the boundary condition. Let's give the extra space, especially for this boundary condition, because it's rather important. And then I will write down this Ti, rho I, again the rho, and also there is transport coefficient, kinematic transport coefficient, which is actually thermal diffusion coefficient. And more precisely to say, not thermal, but entropy diffusion. But there is, if we go to precise denoting, but actually it has a nature from the thermal diffusion coefficient. And here we have this ds by dr. And it's important to mention that these derivatives is taken at r equal Ri. So this is actually the term which determines the heat flow due to the variation of the entropy. And on the boundary or variation of the entropy could occur only in radial direction. But finally, it's depend on the input or output heat flow. So we made this output or input heat flow flux like Qi, and because this is not complete heat flux, but the normalized heat flux, and we normalized this heat flux on the area, and the area of the outer boundary is of course the spherical surface. And it's obvious that its area is equal 4p Ri in square. So if we have this flux which enter in the boundary, what means enter? What means that it supports the convection. How it can add to the convection. So in our term, it should be greater than adiabatic heat flux. So if it's this flux, normalized heat flux, of course, if it exceeds the adiabatic heat flux, then this heat flux working on radial direction. In opposite case, if it's less than adiabatic heat flux, It's acting against convection. It's actually stabilize this place. And in terms of the inner boundary, we always have this flux contribute to the convection. Because this heat flux could be, first of all, of course, due to the cooling of the planet, but maybe more important contribution could be from the compositional difference when the heavy particles are descending on the inner core and lighter particle is going up. So actually, it's it's always positive. But what means positive? If we consider the adiabatic heat flux, so it can be represented by this simple formula. It depends only on r, on the spherical radius, and of course we are taking these derivatives. We are taking this derivative at the inner boundary. And you see that here we have plus, but this gradient, because we have on the upper, the more densely we are going into the liquid outward core, the more temperature is. So it has negative gradient. So this term, if we calculate it precisely, this will give negative. So it will be just the part which is removed from the total heat flux. So this is the total heat flux, and this is adiabatic heat flux with minus sign. So actually here we have a difference. Let's just clarify it. So it's just delta Q E. Maybe that's true. Right. Of course, divided one. So this is constitutes the formula for 6C. Yes, of course, in the same way, in the analogous way, we have the same similar boundary condition, but on the outer boundary. So on the outer boundary, we write it like that. The outer rho outer K is by TR. Let's stress that this K is small K. This is capital. Let's just stress, just for you to understand that it's actually different values, but they of course related one to each other. But nevertheless, originally it's slightly different. And then we have proceed further. R equal R O and equal. Of course, here we have output heat flux RO squared, and then again this K, capital K, and adiabatic temperature. But what? But oh, sorry. This is direct. Not. Okay, this constitutes another delta Q O. Just for your convenience and better understanding, I added this term, just for you to understand that we have not, from this formula, we actually have the, if it's with positive sign, and this heat flux is larger than adiabatic one, then we have positive contribution here. And this positive contribution corresponds to the support of the convection. But if we consider the outer core, if we consider the outer core, then this is again the same rule, but from the recent experiment, they found that perhaps this is smaller than 0. Just say it. Perhaps this is smaller than 0, and this one is definitely more than 0. And this, when it's smaller than 0, it stabilizes the convection, actually remove. And here it's, of course, in favor of the convection. Let's support convection. Another situation, for example, on Jupiter, in Jupiter, this one is the most important. Oh, no, sorry, this one, which is output. Here it's stabilizing the Earth, but in Jupiter it's in reverse order, and it's produced the largest magnetic field. Okay, so we finished with this boundary condition, which is related to the entropy, quite important. Then we should proceed to the boundary condition for velocity. Let's write them down. And this is, here we have 2 boundary conditions. For velocity, we have 6 boundary conditions, because each velocity has 3 components. And we have component on the outer boundary, on the inner boundary, so it will be 6 boundary conditions. And it's interesting to mention that the order of the Navier-Stokes equation, from which we taken this velocity, is the equation effectively of the 6th order, because there are 3 equations, 2 orders of magnitude each. So there is a match between the necessary boundary condition and Navier-Stokes equation. And also there is a boundary condition on the entropy. It's one more equation and 2nd order. So we need to add 2 more boundary conditions. So now we have right number of the boundary condition. Let's just write down the boundary condition for the velocity or Navier-Stokes equation, if you like it more. It could be written like that. This at r equal RO. This boundary at r equal RO. It can be noted like just VO. This is actually the velocity with which mantle is rotating. So we supposing that we are, if we consider Earth, then we are in the frame which rotating together with mantle. And in this frame, of course, frankly speaking, this velocity is not precisely 0, because actually there is some influence. But nevertheless, the mantle is constitute more than, I don't remember exact figure, but about 80% or even 90% of the all the mass of the core. And especially we should consider in terms of the momentum, because you see that if we consider the inner core, okay, if we consider the momentum here in the core, we have some density. So to understand how this law is working, we should consider the momentum, because the second name, and maybe more acceptable, the second name of Navier-Stokes equation is momentum equation. What does it mean? It means that the product of the velocity on the distance is important. You see that here in mantle, you have a larger distance than here in the core. So the velocity, correspondent velocity, Of course, in inertial coordinate system, in which we actually then go, it's much more than here. So if in terms of the mass, the difference is that about maybe just 20% is here for this boundary condition, and 80%. In terms of the momentum, it will be just, I don't know even exact figure, but less than 10%. So at least in the, with accuracy of 10%, and it's quite good accuracy because, for example, we also use this accuracy in estimation of the density. So here we have just 0. Of course, this simplifies stuff a lot. However, there is another boundary which is correspond to the R equal Ri, R equal Ri, and here we can denote it like Vi. And this is not necessary 0, but of course there are some models which regard it like 0, because the differential rotation of this inner core could exist. Of course it's small, but in some sense it's enough to produce some velocity, shear layer, and other structure. So to make the right things, of course, we should take into account this value, but of course, it's not so big, and it's in spherical coordinate system can be written like that. This is actually cylindrical radius. Cylindrical radius, and it's also contain relatively small extra omega velocity, which is in our mantle rotating system is rather small one. And here we have a direction only in azimuthal direction. So we finish up with this. Here we have 6 boundary conditions, as I already told, 3 from here on the outer boundary, 3 on the inner boundary. And this original number of this formula is, okay, I just omit 4. It will be 6, A and B. Of course, from chapter 4, I put 4 here, otherwise it's not fit. So we completely formulated our system, and we write down all the necessary equations, but we just forget about the gravity potential. So we very effectively combine it in the effective pressure, but if one would like to some occurrence to understand how this gravity potential is working, he just can solve this equation. Then he have a reduced pressure, and this reduced pressure together with reduced gravity equation, which look quite simple. It's just Laplacian of gravity equal to P G. Here we have rho P, known thermodynamic. It is the density under constant pressure. And then we have this P, exactly this P which appear here. And then we have density density derivatives on R with constant entropy, of course multiplied it by entropy, which is somewhere here, this entropy. So this is the equation for the gravity potential, from which we can find it after we found the pressure, after we found this entropy. And so if we would like to have the gravity, then it's constitute for B, yeah, formula. And of course, it's also require boundary condition. And boundary condition in this case are quite simple. And they look like that. It's a formula for 6EF, for 6E and F. It's just, as already told, this is the most important on the boundaries is radial derivatives. And of course, so we constitute very simple boundary condition. Du by dr at two boundaries, at both actually boundaries, at R equal Ri and at R equal R naught, they simply is 0. Okay, I formulate everything, but I forgot one thing. Maybe you know who follow my previous lecture, maybe he said that what I forgot. Which condition I forgot one. Rather, I don't know how to say important it's or not, but which condition? If you follow my previous lecture, you can answer this question. I forget one thing. No, it's global condition. If there is boundary condition, there is local condition, which we have the differential equation. But here you see that the boundary condition for the entropy, this entropy, both are in the derivatives. And usually, if you use derivatives boundary condition for second order equation, you should have an additional condition just to determine all this stuff. What this condition? I wrote about, I spoke to you about it. Can you? Just see your previous notes. Okay, I'll give you a hint. 4.3b formula 4.3b. So did you found? So this is the actually integral condition. As already told, if we have the boundary condition which formulated on the derivatives, here we have boundary and derivatives of it. So in this case, for example, when we have Laplacian, at least for the very simplified case, it has constant, its solution constant, and 1 over R, Laplacian solution. If we take the derivatives, we remove constant. So we are out of one free constant. There is only one free constant. And to get another free constant, we should formulate the integral condition. Let's put it maybe here. It's not so big. There is integral in all space. Okay, I will not wrote here that it's in all space. This is integral from the relation, which actually it's related to this. So it's very close to it. And actually this is integral of entropy times rho, and in this case, of course, adiabatic. And all over the space, all over the liquid core, and it's just simply 0. So actually this condition is that the weighted entropy is declining from the, because this is the deviation from the adiabatic state. And if we integrate all this deviation from the adiabatic state, it finally should give 0. So this derivatives not only mathematical help to this boundary condition, but it also has physical meaning that the total deviation from the adiabatic state should be 0. And so this is a physical meaning of this. Mathematical meaning is, of course, to make the complete system of the condition, which allow us to precisely to resolve this equation. So there is two meanings of this stuff. Okay. So actually we formulated everything. What is constitute derivation of this equation? Okay. Okay. And on the next, we will discuss how precise is this system and estimate from the nonlinear approach the characteristic value of the system. But now there is a time for your question. Okay. Oh, sorry. I just remind you once more that we can resolve a system for the velocity and entropy actually separately. And then if we need some gravity potential, we can resolve it after that. So there is a good point of representation via entropy that we can resolve all the system, which is in calculation and so on, quite simple, relatively simple. It's actually it can work almost in any planets and even some stars, but it's relatively simple and it's almost like in Boussinesq form, very close to the Boussinesq form, and it's just slightly more complicated. And this complication is that we have, instead of the divergence at v, we have the divergence of this momentum. It's not so big deal to treat it numerically, for example. And the other difference is in the boundary condition and this global condition. I should number it. Okay. So please, your question. Okay, is there any questions? Okay, everything is clear? Is everything clear? I hope so, of course, that everything is clear. Okay, is there any question? No? Okay, anyhow, this text of all this stuff will be available. So, huh? 451? On the screen. Yeah, okay. 4.1, yes. It's just collection of all equations. 4.1, it's initial equation which we have, all of them are actually 4.1. It's just in this chapter, it has 1, 2, 3, from A to E. So all this equation are the initial equation, And this is the initial equation, as I already told you. There is the continuity equation, then we reduce it. There is the gravitational equation, then we again reduce it. And there is equation of state, and we reduce it to the dependence on the pressure and entropy only. And of course, there is the equation for the entropy. Here it's present in initial form, but what I finally show, it's not for entropy itself, but only for deviation from the adiabatic entropy. Everything deviation from the adiabatic, deviation from the adiabatic density, which actually drives this buoyancy force here, which originally from here. And of course, only velocity has its own meaning. All the other stuff, we reduce it to the deviation from the adiabatic state. Yeah. This one. Hmm? Sorry? Yeah. We express everything in pressure and entropy. We express temperature variation, we express gravity variation, we express what else? Okay, everything excluding velocity. Velocity is playing its own game, but everything excluding velocity is defined in terms of the not pressure itself, but the deviation of pressure from the adiabatic state, and also not entropy itself, but the deviation of the entropy from the adiabatic state. Because of course this deviation is very small. Mm-hmm. And all the game is around it, because the deviation is just roughly, say it's 10 to minus 3%, 10 to minus 3%. So actually it's 10 to minus 5, something like that. So this deviation is very tiny, but nevertheless, namely this tiny deviation from the adiabatic states creates the convection.
Mm-hmm. So how to choose the rho A?
Rho A?
That's 4.1, first term on the right side.
This one?
Yeah.
This rho A is adiabatic density.
Adiabatic density.
Everything is adiabatic here, excluding the variables.
Okay.
So actually this is the approximation, almost adiabatic approximation. So we are working very close to the adiabatic approximation, so we are getting this result like that. Okay, one more question, please.
Approximation. What is the motivation for assuming an adiabatic approximation? Is there any validation for assuming?
It's very important meaning. It has very important meaning. If you want effectively to solve the system, you have to do that. Because if you will not use this approximation, for example, even in the case, usually people regard that it's normally not to use entropy, so people somehow avoid entropy. They didn't like it, I don't know why, but they prefer to work in the ordinary pressure and temperature, for example. And I devote this, in the next chapter, I will estimate the accuracy of this almost adiabatic approximation, and also I estimate from nonlinear point of view typical values and compare with those. But after that will be special subject where I show that if you use pressure and temperature instead of pressure and entropy, you have much more complicated equation. They even, I don't know, it will be hardly possible to resolve them in numerical as well, much more hardly than that system which I showed here. So this is a very strong motivation to have the almost adiabatic approximation. And another point is that here we just slightly change the form, and it's taken into account all the effects, even with rather big variation of the density. So in few words, it's like that.
For entropy, we have separate
equation, suppose, what's the difference? Suppose we consider there is the difference on pressure and the temperature, but entropy can be calculated to separate equation also.
It's maybe not right way, because at least in this problem, I don't know, maybe another problem work another, but in this problem, the major essence of all this problem is that everything is near the adiabatic state. So if you operate very near the adiabatic state, and the adiabatic state is initially defined by entropy. So adiabatic state is just the entropy is independent on the space. It depends only on time. I mean total entropy, of course. Not the variation, not everything, but the total entropy. So actually, this is a very good approximation, and it has very high accuracy. So actually, of course, in some applications, maybe many applications, technical applications, it's more convenient to use the temperature. But namely in this application, much more better is using the entropy variable. Because even the equation, as you show in one lecture, because even equation becomes very complicated. And you can, maybe it's possible to resolve them, of course, but it's much more effort. And not so precise, actually. It's also important.
Third, second equation from bottom, entropy equation.
Yeah.
Right side is operator operating on gradient of
Yes.
temperature.
Yes, it's temperature, but it's just initial equation. The final equation, which I wrote here, we just here it is. You see, you actually rearrange this equation that instead of the temperature you have entropy.
Okay.
You just rearrange the equation in the way that it's, and here, of course, not the initial co-plane game. Here there is adiabatic flux, and all other things are accumulated there.
Is it T or it is S? Is it T or S? Just I want to know.
Yes, here we, as I don't know, where is here to get this equation?
Yes, it should be not T, but it is S.
Yeah, we expand in a few words. We expand T in terms of the pressure and in terms of entropy.
Oh.
And then eventually contribution from pressure is very small.
Oh. Okay.
So we neglect by contribution of pressure and left only with entropy.
Okay. But T equation is not here.
This is sort of the game.
Okay. The T equation is not here. What is the T equation? T in terms of pressure and the entropy?
T equation, I'll write down. Okay. I will write down equation for T. Okay, well, let's put it here. It's just thermodynamic equation for T.
I understood.
Equation for T, and it's can be written like it's our previous formula.
Yeah, I have seen this.
This equation for T, or more specifically, is the deviation of T from adiabatic state. So T over T, it's small variable, and it's expand in two terms. One is partial derivatives from T under the constant pressure, multiplied it by pressure. Of course, the deviation from the adiabatic state. And the next
minus
next term, here it's plus
TS
plus
and TS.
TS times S. And this is actually formula 4.2. 4.2 G. And the play is that this term is so small in comparison with this term
Yeah, yeah.
that we just simply can cancel out it.
Okay, okay.
And then we arrive to this.
Uh-huh, okay. So in same equation, rho into t, is it rho into t? It is non-linear contribution, right?
Yeah, this rho into t is also important because it's the same game. Again, we neglect that and keep that.
Oh,
And eventually this deviation of rho is coming to the Archimedean force.
okay.
This Archimedean force or buoyancy force.
Oh,
And it depends again only on entropy.
okay.
Actually, the main play here is that the pressure against entropy contribution is negligible.
Negligible, okay. In that way.
So the main plane is around this stuff.
Okay.
So it's not wise to keep pressure because it's small. More precisely, of course, not pressure, but deviation of the pressure from the adiabatic state.
Yes. Okay. All right.
Okay, thank you. Okay, it seems we finished. Okay, it's not my invention. It's invented by Braginsky in 1964, something like that. So it's quite old stuff. But nevertheless, it's still working. But unfortunately, not so many people proceed in this way. This is quite the right way, but not so many. Of course, the most gifted person, like the Braginsky, Roberts, Glatzmeyer also use this approach very much. But yeah, I got the impression, but that people just afraid. Because the things I presented here is just about the temperature contribution, but there is compositional contribution, which constitutes the second derivative, and the much more complicated boundary condition. Because in boundary condition, when you have addition, not only temperature, but the diffusion of the light consistent. So its equation becomes much more complicated. But nevertheless, it's possible to push this approach. And in Braginsky, okay, even Braginsky and Roberts wrote the paper, which still named 100-page paper. They wrote about 100-page paper in GAFT. Yeah, it was special issue. Here they considered old stuff. Yeah, please.
So in the mantle convection, can we take the Coriolis force effect will be there or?
Yes, the Coriolis force will play a very important role, of course. It's one of the central force. Actually, especially when we consider convection, after my next lectures, of course, I will be only about convection speaking about. And if we consider convection, there is, from my point of view, maybe one of the main breakthrough of humanity.
Oh.
Because this convection system, which I wrote here, was resolved almost precisely. You see that this is 8th order system, because the 6th order in Navier-Stokes equation, 2nd order is equation for the entropy, and so it's 8th order system in partial derivative. And it's possible, due to the smallness, relative smallness, if we take the ratio of this, maybe better to put here, if we take the ratio of for example, uh, for example, of viscosity term to the Coriolis term,
Coriolis.
we exactly get the Ekman number. It's 10 to minus 15. So, and it's effectively enter like the small parameter near high order derivative. From one point of view, it's a very difficult things to calculate. But from an analytical point of things, you have just first using that stuff, you work on the boundaries. And on the boundaries, there is a thin layer which has a thickness of the square root from Ekman number. And here problem becomes two-dimensional actually, because we can work only in the boundary layer. And you can almost precisely to manage with this Ekman boundary layer. Then there is another, not boundary, but shear layer like that, Taylor column, maybe you hear it, where the major convection occurs. And in this, again, we can expand an Ekman number. And finally, the final thing is that we reduce this 8-order partial derivative system just to one ordinary differential equation, one second order, just one second order differential equation. Of course, with plenty of parameters, because every parameter means the picture which we involve from this stage. But I think that maybe it's one of the main achievements of the humanity, of the mind, or whatever you like. It was started by Bousset. Then it was, of course, I will speak in my next lecture. But it's, I also made some contribution to that. Okay, so but nevertheless, from my point of view, it's quite impressive that so complicated system we reduce it just to second order ordinary differential equation with, of course, putting on this boundary condition, and so actually it depends only on z coordinate eventually. The final system, which of course the characteristic system, not the, which involve plenty of parameters. Of course, it's also linear solution, but nevertheless, it's quite impressive, and it's possible to compare it with the full numerical approach, and accuracy of this asymptotic solution is very good.
The fluid is only thermally conducting, not in the mantle. The fluid is only thermally conducting, right?
In the mantle, there is some model that assumes some convection in the mantle.
Mantle convection, right?
Yeah, there is model of the mantle convection, but it's very slow convection. Much more slower than in the Earth core. In the Earth core, of course, convection is also not so fast. It's just a few millimeters per second, even less than few millimeters per second. But in the mantle, it's even slower. So the typical time of the convection in the Earth is about 1,000 years. So we just can directly see how magnetic pole is rotating about the axis. The typical period is about 1,000 years. More precisely, 500, something like that. But in the mantle, typical time, million years.
Okay.
So it's quite slow. And it's maybe not precisely convection, because there is some intermediate state between the rigid, at least on our time scale, we can treat the mantle like the rigid body. But of course, on the larger scale, it will be treated like a liquid.
So it means the convection is slow because of the rotation, right?
No, it's not. It's not dependent on that. Independent rotational rate also have some stabilizing effect, but this stabilizing effect is the Taylor condition that in the direction of the axis of rotation we have only small changes, but we can have dramatical changes in the cylindrical direction and in a radial direction. So this is perhaps the main point.
So we are getting volcano liquid from the mantle or from
Sorry?
volcanoes liquid, lava,
I don't.
lava,
Lava
magma,
I
lava.
see.
That comes from the mantle or somewhere else?
Yes, of course, the lava flow and other flow, of course, they on the, I don't remember exact numbers, but somewhere, if you go down by about 100 kilometers, or maybe some tens kilometers, so you will have this higher temperature. It's a quite known experimental fact. If you are going down, then you reach the temperature is rising, and there is some boundary where the temperature is rising so much that it becomes sort of the liquid, not precise liquid, but sort of the liquid. And because this process is somehow chaotic, so we have at some places very thin layer or very of the rigid substances. And in some place we have sort of the breakthrough, and here there is this event appear. Perhaps it's even inner core could be responsible for that, because from the inner core we have some sort of the, not precisely fluid core maybe, more precise to say the fluid core. There is some, there are many theories, but about this convection and mantle, about how it's connected with the lava flow, with volcanic eruptions. But frankly speaking, there is no firmly state theory. Most of them are just suppose some chaotic behavior, something like that.
So what is contribution of rotation of mantle to the Earth?
You mean that rotation of the mantle?
I don't know. What is the contribution? For example, Earth's outer core, due to the rotation of that core liquid, we are getting the magnetic gravitational field, for example. So similarly, what is contribution of rotation in the mantle to the Earth?
Mantle is rotating at least on the time scale, which is below some maybe 10 or maybe even hundreds of thousand years. On the time below this value, we just can suppose that the mantle is in the rigid body rotation. And of course, on the more longer age, up to million, billion, whatever you like, maybe some thousand, maybe hundred times 100,000. I don't know. Nobody knows exactly. But on the larger scale, it can work like the liquid. But in any scale, there is no way to produce magnetic field.
Okay.
In any case, just because the very low conductivity. But in the liquid core, the conductivity is rather higher. Just because it's just a ferrum. It has very high conductivity. So this is the birthplace to produce magnetic field. And by the way, the energy of magnetic field is million times greater than the energy of the convection itself. So this is a very effective producer of the magnetic field. It's even has this tiny value of the convection, and it's produced huge magnetic field. In this term, the magnetic field of the Earth is much larger than the Sun. While if we consider new numbers, on the Sun we directly measure kilogauss. On the Earth we measure the about Gauss field. It seems that 1,000 times less. But if we consider the energy, then the energy of the Sun's which is, we also directly see the velocity of the Sun. We see how we even can understand how it's working inside the Sun, because there is an analog of the earthquake. There is a sunsquake, and they are of course much more intensive than earthquake. And just using this sunsquake, just to figure out what is this inside the Sun, we can find the velocity, we can find density, we can find everything, even more precisely than in the Earth, because only by the reason this sunsquake is much more intense. And so eventually we can easily estimate it how much is the energy in the kinetic, in the velocity and the relative velocity, of course. And it means after that we can draw the conclusion that this kinematic energy is even greater than magnetic in the sun. But in the Earth, the reverse situation. Not simply magnetic energy greater than kinetic, but million times greater.
That is the reason. It means the Earth outer core rotation will not affect the mantle rotation, right? Earth's outer core rotation and mantle rotation, do they have any correlation? Otherwise, they are independent.
Yes, of course, there is also correlation, because actually this problem is very much linked to the length of the day. Because actually, of course, we suppose that the angular rotational rate in this formula that's constant. Of course, it's the simplest and in some way, but it's not constant, of course. It's not constant, and it's changing time and changing the direction. Direction, you have this variation of the angular rotational rate of the. There is the. I forget the English name. Due to the influence of the moon, for example. This is tide effect, which play rather sufficient role in changing of the angular rotational rate from the moon. And by the way, there is almost the same tide effect which we have from the sun and from the moon. Moon is much smaller than sun, but it's much more close. So eventually, moon and sun has comparable effect on the rotation of the Earth. And of course, on the ocean, on the sea, that we have this changing of the in the tides and so on.
Means we had to study both models separately. Earth's outer core model separate and mantle convection separate. Can we combine both the models?
No, you are not right. They are not separate. They are quite tightly linked. The reason why the magnetic field energy is much more greater than kinetic is not working direct. It's working in the way that maybe you know that if we have the velocity in some direction, then if you have the magnetic field, so the interaction is V cross B. V velocity, B is velocity vector, B is magnetic vector, and V cross B. So the main effect is when they are perpendicular. And when they are almost in the same direction, the effect is actually cancelled out. So this thing is working like that. Not the velocity diminish, but the velocity could even very small. But the magnetic force, magnetic field has a tendency that it tends to be along with the velocity. And the more they are following the velocity, more they parallel to the velocity, more value it can reach. So eventually, if there is such a tendency, it can reach tremendously big value, but staying almost parallel to the flow. And it's eventually, so this working in some tricky way, not direct.
Not direct.
But the dependence is very strict. Because maybe one of the first work of the Braginsky was almost axisymmetric dynamo or something like that. So if we have some symmetry and it's strongly related to the flow, then we could create very strong magnetic field. And vice versa, it's like on the sun, we have the magnetic field which is not so strongly parallel to the kinematic velocity. Then we have this magnetic field in terms of the energy, of course. In terms of the energy, in terms of the absolute value, of course, it could be big. But in terms of the energy, it's small. Maybe not small, but of order of magnitude.
Okay, thank you, sir.
Okay, thank you very much for the question. My pleasure. but maybe we'll have the break because we spent 2.5 hours. Oh no, 1 hour and a half. Okay, shall we start? Okay, please switch on. It's working? Okay, thank you. Okay. For actually in our previous lecture, which was extended 1 hour and a half, but we seems fully understand how this equation appear almost in all those adiabatic approximations, that it result in now your Stokes equation and equation for the entropy, and this are in fact 8 equations satisfy to 8 boundary conditions. So actually we formulate everything. So now we can discuss, and there is special separated paragraph about accuracy verification by nonlinear scaling actually. We will proceed with nonlinear scaling, and after this nonlinear scaling we obtain the characteristic value of all the parameters, and we will see that the initial assumption which is shown on this picture, that initial assumption on which all this system was derived is satisfied. So this is our goal. To reach it first, let's remove. You just write down the name of the chapter, 4.2. 4.2, accuracy. It's the name of the chapter, accuracy verification by nonlinear scaling. And actually we will do very simple things. I'm removing this equation, but of course we will refer to this equation somehow. Nevertheless, they are kept in U, so I will be referenced on this equation of this equation system when proceed further to this estimation. And quite natural estimation to understand the typical value of the problem is just to involve some nonlinear term, because from linear term it's quite difficult to make estimation, because linear term could be balanced only at one level. So you just balance one value with another value, so you can balance only values that exactly equal to each other. But in nonlinear situation, it's much more better case, because we can involve in balance nonlinear term, and this nonlinear term will give us the various results which are directly related to the preferable balances and so on. So actually this situation is necessary to use solving any problem, because actually if you state the problem in the way that it's difficult to reach the proper solution, it's not the case. It's better to avoid this situation. So let me state the system the system which was just removed, this complete system with all the boundary condition and everything, is formally similar to the well-known system obtained in Boussinesq approximation. For example, you can see work of Glatzmeyer, Roberts, Christensen, and Aubert, and many others, including myself. The similarity is especially clear in the superadiabatic entropy. For the superadiabatic entropy, which is written here, but let us repeat it in number. So superadiabatic entropy, we will denote superadiabatic entropy by just small s. Then the s itself is s, and so that it is derivation from superadiabatic entropy means like that there is adiabatic entropy, and we consider some general entropy, and so eventually the deviation, this from this is quite small, but it could be dependent on coordinate and time as well. While maybe if you remember from my previous lecture, this adiabatic entropy depends only on time, not in space, but only on time. So, and eventually we can get this expression, which is just repetition of what I showed in the previous lecture. There is expansion coefficient, there is the adiabatic density, then we have pressure, not the pressure itself, but normalized pressure, which is on top of the adiabatic pressure. So it's just near the adiabatic pressure term, which is actually the difference. And this only this play a role. And then there is a contribution from the temperature variation. Temperature variation is this contribution from the temperature variation could be represented like that. We divide Cp by Ta, and we have such a value which we regard like a temperature variation. We use slightly another, not slightly, but other values than we used. Frankly speaking, in our previous lecture, we didn't use any notation for this variation of the temperature. We just say that this variation is small and put it everywhere. But here, because we want to estimate some sort of the real values, so we just made the special notation for the variation from the temperature. So actually, this superadiabatic entropy from actually it's coming from formula 4.22, and it will be considered more below, and is substitute to the formula 4.48 and 4.78 formula, which we just put the most recent formula. One formula is about the entropy equation, and another from the okay, so and actually in this formula we already neglect the superadiabatic pressure, which is again just I remind you that just to remind you that this theta in our case is equal T minus TA, and the pressure, this pressure, small pressure, is in our case P is equal capital big pressure minus adiabatic pressure. It's just to remind you. And let's number this formula. This is just repetition. Here we can put the dot, and this is the number of formula 4.8 A. Okay. So actually, to get this relation one, we neglect, as already told, this superadiabatic pressure contribution compared to superadiabatic temperature, and the system obtained after such a substitution is practically equivalent to the Boussinesq system. I already showed you this Boussinesq system, and I will not repeat it again. And a small deviation from the complete equivalent is only in the boundary condition and in the fact that the positive heat source replaces the superadiabatic source QA from formula 4.8. So superadiabatic in our is replaced, and the condition of continuity divergency condition replaces by anelastic condition, which is just the divergency of the momentum rho over v. Everything that I've spoken about, I just remind you, and this approximation is true for the obtainment almost adiabatic system. This previous my approximation, which I wrote down on all these pages. So only when the following conditions are satisfied. This condition is written here, but let me write it down and comment. The condition is like that. Here we start to involve some typical value. We just can write down this condition and the main condition under which the previous system was derived, that the ratio of Cp over adiabatic T in terms of the temperature. And here we have new notation star. I think that it's quite a convenient notation just to mark characteristic value. So what is following after the situation when we have this characteristic value, and so this is the deviation from the adiabatic temperature like this, and so it's also we just mark it by cross. And also there is a contribution of the pressure, but the temperature contribution is much more than contribution from the pressure to the buoyancy. And it's written like this, and it's actually depend on the characteristic value, but not density. It's true, I should stress that this is the deviation of the density from the adiabatic state. So this deviation is quite tiny, but in terms of the adiabatic state, it could be quite substantial actually to drive all the picture, because actually this deviation of the density actually drive everything, because when this deviation, for example, when it becomes some place becomes hotter, its density becomes slightly less, and then its place goes up. So actually this works like the main source of the convection. And the previous system which I showed you on the screen at the finish of my previous lecture is based on this assumption. Let's now to prove it. Now we try to prove this assumption. Rosta. Pista, sorry. No, pista, yeah, you're right, yeah. Sorry. Okay, sorry. Thank you for, it's my fault. Yes, of course, pista. So again, sorry, I spoke wrongly, because when I wrote this roster, I start to think that it's about buoyancy, but it's another game. Thank you for correction. I just write wrongly. Sorry. So actually here we set the condition that the variation in the buoyancy due to temperature, typical temperature, is much more than due to the variation of the pressure. So in this all terms, as already I showed you, we neglect corresponding term and keeping only this term, which is responsible for this. So this is the point, and now we show how to prove it, starting from the typical value. For the typical superadiabatic value of the temperature and pressure, so we should understand how to get it. And in order to estimate the accuracy of results of the previous section, the feasibility of formula 47b and this new formula 47 for 7b, for 7 and for 8. This A and this for 8b. We will estimate the typical scale, amplitude, or average from the module. Actually, this is has a different name, this value which is marked by star. So it has many names. And so we estimate this value of the main suprabatic quantities in the Earth's core by the order of magnitude. This is actually the case when of course, there is different way to estimate this characteristic value. And before this work, which was done by me and my co-author, it was some works who estimated also this typical value, but from another point of view. They involve, first of all, the boundary condition. And following the boundary condition, they tried to estimate all the stuff. But on my view, it's maybe not so good way, because actually, if you remember the boundary condition, especially for entropy, they are somehow dependent on the buoyancy layer of the boundary layers, and so everything that it's known to involve the true value term. Unlike the Anufriev and Kupel, Christensen and Albert, we will following actually my work with Chris Jones and proceed from the fact that the typical quantity should be practically independent of the uncertainly determinant transfer coefficient and boundary condition. You know that if you start from the boundary condition, then especially in the entropy case, you should involve sort of some diffusion, some transfer coefficient, which is quite poorly known. And even we can state that this viscosity effect, which is linked with these boundary layers, it's a diffusional effect if you consider the entropy equation. So this play maybe not so main role, especially in the bulk volume of the liquid core. Of course, it plays some role on the boundaries, but now our goal is to get the characteristic value well outside of the boundary, in the main body. So, this for well-developed convection, the typical convective time, T equal, we'll consider typical convective time T star, and it's obviously equal to the typical radius. I should stress this is not the radius of the problem, but this is the typical radius which is actually working in derivatives. So if we take the derivatives with some space, not necessarily longitudinal in any direction, so there is some characteristic derivatives, and we just obtain this typical scale from these derivatives. This is not connected to the geometry of the problem. It's connected to the, actually, as I will follow in the following, I'll show that it's, actually it's expressed okay. Actually, it's expressed through both the typical size and the typical radial velocity. And from the energy considerations, if you see in the previous section, we equate the rate of change of the kinetic energy to the typical work of buoyant force. Okay, for that we see the, okay. For that we see that the, if we equate, okay, let's first put on the first place. Here we have the typical scale, and then we have the inertial term, which includes typical density. Then it's include square of the velocity. You remember u grad u, so there is square up here. And everything is divided, if we consider in terms of time, it's divided by t, and we expand this t like that. We divide over t, but t is equal just typical size on velocity, so we can put here again typical size of velocity. So we have this manipulation, and this is also if we multiply by the, actually we have this relation, if we multiply by the velocity, the equation of the Navier-Stokes, and the major term is the inertia term, and we estimated it like that. And also there is the Coriolis, there is buoyancy acceleration term, so we just introduce special notation for the acceleration of the buoyancy, also with star. This is acceleration due to the buoyancy. And in our notation, which we adopt in our previous system, this work of the buoyancy force, it was obtained by the just multiplying by v. And then this also there is the main drive, which is actually this entropy value. So it's, let's number this formula 49A. This is the starting formula for the estimation of the typical value. And here, again, I remind you that the index star marks the typical value. For example, let's now just consider some example which is going from the other estimations. For example, this R star is approximately equal it's approximately equal 8 Kelvin, 8 Kelvin per kilogram per mass cubed. Oh, not cubed, 4. Mass 4. In horsepower. Okay. Then actually it corresponds to the given Archimedean acceleration. So actually it corresponds this Archimedean acceleration, or the if you like buoyancy acceleration, which is equivalent to expansion coefficient, adiabatic temperature, then the density, and this is how we have module of the gravitational potential. Of course, it's about the adiabatic part, and also divided by Cp. So in fact, we can have some very good estimated part for this value. So then, since the Coriolis force does not do work, it is not included in this relation. So we are not with Coriolis force because it does not create any work. And this is actually related to the work of the staff. So dominating the equation of motion for 4R, it balances with the gradient of superadiabatic pressure, and we estimate the force balance by taking the, actually to make this estimation, we should estimate the force balance by taking the rotor or coil from 4.4a equation, which is actually Navier-Stokes equation, and getting rid of the pressure. So after that, we have the following two estimations. one which is connected with pressure and another with Coriolis force regarding the pressure and the with Coriolis force which regard again this buoyancy term. So we have the estimation Coriolis force itself. Of course, more precisely to say this is not Coriolis force, this is Coriolis acceleration. So it's from one point of view, it's equal P star over outer core. Because here when we take the derivatives, it's only in that direction and it's just slightly changed in that direction, as I already told. So we have here this P, RO, and now density. And then another relation we have, which is related to the buoyancy term, rho omega V over outer core radius, and then it's everything balanced by the buoyancy acceleration, which well known, as well already told to you. Divided by typical size R star. Okay, this is equation 4.9 BC. So here the radius of the outer core RO, which is much more than R star. It's necessary to know that RO is much more than R star. Just because this is the real radius of the problem, and this is value radius which appear in the derivatives to the different values. So in accordance with the Taylor-Proudman theorem, which was commented regarding to this flow by Braginsky and Roberts and Bousset in 1995 and 2002. And so we complete system 49 by the estimation which was done by myself and Chris Jones in 2002. So 20 with something less ago. The balance on convective heat transfer and superadiabatic heating from the integral of the general heat transfer equation 4.778, which is of course related to the entropy. This balance can be written by rather simple formula. Typical rho, typical temperature, capital temperature mean adiabatic temperature, of course. And then here we have typical velocity divided by RO, and then we have typical entropy. And this is the final formula for David 4.9D. Okay, actually we have three equations and three unknown. What is the unknown we are looking for? The unknown is velocity. Then we have all this rest is unknown is velocity, which we want to find. Also unknown is the radius which we have, and another unknown is the deviation of the entropy S star. So for all these three unknown, after all this manipulation, which also listed here on this table, we are resulting in the following relations. So we just involve all the stuff, and eventually we get maybe there is maybe not so correct representation because some values with star are exactly known. For example, this rho, temperature, and some value that we just estimated, this typical velocity, entropy, and radius. Actually, we estimated only 3 values. And the rest of the value, including that which we add with the star, are rather well known. So we just take them from the independent researchers. So let us determine for the obtained system, which consists from for 9A, B, C, D. Actually, in this system, we also have pressure. So actually, there are 4 unknown and 4 equations. These 4 equations are all numbered with 4.9. So from A, B, C, and D. So actually, there is 4 equations and 4 unknown. Let me stress again that unknown is deviation of the pressure, deviation of the entropy, and velocity itself, of course, unknown. And another quite important parameter is the typical scale. This one, which is much less than the scale of the problem, initial scale of the problem. Okay, let's determine from the obtained system typical superadiabatic quantities. I don't know, is it enough? Okay, I'll try to fit in below as a result. So for V, we obtain root of the 5th power of Rho in cube. Then we have this typical flow in squared. Then we have Archimedean acceleration or buoyancy acceleration in squared. Then there is density in 4th power, temperature, adiabatic of course temperature, also typical in 2nd power, and there is omega. Okay. And if we put the known for the Earth value, then we have the estimate about 2 millimeters per second. Then we can estimate typical air. Of course, we have the similar expression. Okay, maybe. Oh, maybe I missed one equation. So 1A for 9 B C for 9 D. Ah, it's here. Oh, I didn't write it completely. Sorry. I didn't write it completely. I didn't write it in full. Sorry. Thank you again for my mistake. So this value is equal to just this heat flux, which is well known. This is adiabatic heat flux, and it's equal to this equation. So there is some small addition here. 49. Sorry, I missed this term. So now it's could appear here as well, and it's quite well known. It's just adiabatic heat flux. Then for radius, we have the similar expression again in 5th root. Q squared cube. Okay. And then this is two formula, 4.10 A and B. And the remaining term, this is two term, which is quite realistic. This one of order 2 millimeters per second is rather well known, and it corresponds to the movement of the some peculiarities in magnetic field. When around some thousand years, the complete circle of all this magnetic variation is occur, and you can see it on the geomagnetic variation. And here also there is some size, which is, if we put some typical for the Earth stuff, then it will be equal about, okay, let's put it this way, about 1/10 of the thickness of the outer core. Oh, no, inner core. Oh, outer or 1/20 of the thickness. So it's indeed we satisfy this condition which we wrote previously, because this RO is of order 3.5 to the 10 to the 6 power. So it's 30 times more larger. This value which related to derivatives in comparison with the real geometrical value. And much more simple formula appears for the entropy deviation. Let's put it here. It's just R by rho without any root. Omega. And now, of course, we're using the trick to remove this complexity. We just repeat this value here to make the relation more simple. And here we have O. This is the entropy, and we can just estimate it, and it's about 5 times 10 to minus 6 joule per kilogram and per Kelvin. And pressure, the final value which we will use for the following estimation. The pressure, typical pressure, or more precisely, of course, not pressure, but the deviation from the adiabatic pressure is equal. Again, we use the same trick, and it will be equal. Okay. O rho ta omega and again we represent everything in V, and it's about 6,000 newtons per meter square. So it's just pressure, of course. As a numerical value which was used here, okay, it's not listed here. The numerical value which was just used here, let's write them down as well. Okay, we don't no longer need that, so we remove. And of course, for the estimation of this typical value, we use the value which are well known for the Earth. So we remove the stuff which we no longer need, and to write down this typical values. Okay. The first one, which actually drive everything, this relative heat flux, which is equal about 10 to minus 8 watt per meter square, for cube meter, sorry. Then acceleration, this scaled acceleration, which is scale with correspondent temperature, because actually we are looking for the temperature. It's equal, its typical value. It's about 8 Kelvin per kilogram per meters in 4 power. Then the temperature, also well known, as already told you that it's some 1000 Kelvin, and it's the adiabatic temperature. We just take it like 5000 Kelvin. And the pressure also quite well known. Unfortunately, all these values are all well known, except in this one. This is not so well known, but all these are almost precisely known. Not so precisely, of course, especially this one. This is almost precisely, and this one is with the accuracy of about some 10%. And this also, but this one is known very well. This is typical density, which is for the Earth core is about 10 to 4 kilogram per cubic meter. So our for typical value of known adiabatic parameter in the liquid core of the Earth, and we use them to get these estimations. So let us estimate the accuracy of initial nearly adiabatic approximation. As we already told, now we have everything to estimate this accuracy. And it's accuracy of the basic system, which we write it down on the end of the previous lecture. And so now we use Earth-based parameters, which are all mainly listed in the 4.10 equation, A, B, and so on. Okay, I didn't number it that one. Okay, it's of course 4, 10, E, D. Okay. So if we compare the accuracy of nearly adiabatic approximation for pressure is 10 to minus 8, and comparing the typical value of superadiabatic pressure 4.10 D, this one, the very last one, with the typical maximum adiabatic pressure, this it's necessary to stress that it's capital P. So it's adiabatic pressure, not just deviation. And this maximal adiabatic pressure is well known from the Earth observation, and it's equal 3 times 10 to 11 Newton per square meter. You see here the order of magnitude is 11, and here this order of magnitude is just 3. So the difference is 8 orders. So big difference. So we can state that the nearly adiabatic approximation for pressure is 10 to 8, or maybe in the worst case 10 to 6, 10 to minus 6, if we consider some not maximal value, but maybe not so maximal value, some average value. So the accuracy is 2. So we will draw the conclusion that accuracy is something around 10 to minus 8, which is more than enough for our purposes. Okay. And the ratio of superadiabatic entropy for 10C to adiabatic entropy is even smaller when definition 4.3a and several billion years as a typical time for the change in the adiabatic entropy, and even smaller value. Even smaller value would be sufficiently smaller for adiabatic entropy. S for capitals, something like that. So, and 4.3. Okay, it's related to the 4.3, where we use various temperature and some. So let's just reference on formula 4.3a here. You can take this formula and compare. Thus, the nearly adiabatic approximation has such a high accuracy that it is more than sufficient for constructing numerical analytical models of the convection in the core of the terrestrial planets. Of course, somewhat less accuracy, but nevertheless quite sufficient for the practical model, is the simplified almost adiabatic system, which we again introduced it previously, and the accuracy of the unelastic condition. Unelastic condition is the condition. Unelastic accuracy of an elastic condition, which is just rho over v equals naught. This is accuracy of this inelastic condition. Is determined by subterabatic variation of the density, which controls all this equation from for 10 CD and for 1E, and pressure in accordance with. So actually there is deviation of the density, delta rho typical, and this is actually will be related to the deviation of pressure over the square of speed of sound, and it's just about 10 to minus 4 kilograms to meter cube. So actually, if we divide this value, which we number like 410e, if we divide by the typical velocity, and the typical adiabatic density gradient, we get the value of about just 100 seconds. Just 100 seconds. And the typical time of the convection under consideration in the ratio of formula 4.10b to r, which is about more than 1 year. More than 1 year. This typical, sorry, I removed it, but actually we should consider the relation of 100 seconds and the value which is about 5 to the 10 to 7th second, which is about 1 year. And this is the typical time t star we used before. So you see that this ratio is quite satisfactory as well. So this ratio is about about 10 to minus 4%. So again we return back to this 10 to minus 8 estimation. So accuracy is quite good. So actually, of course, not everything is so brilliant. Just also we should consider that there is a variation in the density. No, okay, and of the later value, 100 second is approximately a quite satisfactory compared to the just 10%, actually 1 promille for centrifugal acceleration. Okay, we now trying to compare with another factor which we neglected. This centrifugal acceleration is accounted to the 10 to minus 1%. It's about 10 to minus 1%. And it's quite clear that it's much more than 10 to minus 4. So again, we have good accuracy. Thus, this 10 to minus 1% is lower estimation limit of the accuracy of the entire system. So accuracy is quite good. Let us now estimate the accuracy of the modified Boussinesq approximation as it was proposed in the beginning of this section. To do this, we assume by contradiction that the necessary condition 4.8 is satisfied. This 4.8, this condition, this necessary condition is satisfied. And then the typical superadiabatic temperature, after all this stuff which we involve from the typical value, this superadiabatic temperature is quite low. This deviation from the adiabatic scale is just 3 times 10 to minus 5 Kelvin. You just have to compare with this one. Here we have 5,000 Kelvin. And this deviation is just, oh, I forget the stuff. It's just 10 minus 5. Again, we get the same relation, 10 to minus 8. So it's in agreement with formula 4.8, which you see on the screen. And without pressure. In this case, the temperature contribution to the entropy, this first term, which is written on this formula on the bottom, is entropy, this term, which is relate Cp to Ta on delta, this term. Okay, let's write it down. Cp theta is 4 10 to minus 6 joule per kilogram per Kelvin. It actually is not so much greater than it should be in agreement with 4.8. And it's less than the condition from the pressure, which is much less. So contribution from the pressure, if we compare this with contribution from the pressure, its pressure contribution is alpha by rho actually adiabatic, or maybe we can put this star here if you like, because it doesn't matter, and the typical pressure, and the corresponding contribution is approximately equal 10 to minus 5. So you see again, okay, the same values of course. Again, you see that it's much more larger than that one. Okay. That's the initial assumption 4.8b, which was on the top one. About the applicability of the modified Boussinesq approximation proposed at the beginning of this section is absolutely incorrect for the liquid core of the Earth, and there is every reason to believe that it will be incorrect for the deep interior of the planets and moon as well. So we start from the inverse assumption, and then we arrived to the contradict. And so eventually we see that our initial proposal is true and our system is quite accurate. Moreover, it is argued here that it is impossible to modify the Boussinesq approximation so that it is valid if, as in the classical version, temperature and pressure are used as the main thermodynamic variables. Actually, you should see the next section after the next section where it was justified. So it's impossible to use thermodynamic as main thermodynamic variation pressure and temperature. So this leads to the fact that the superabatic entropy, which controls the total energy in accordance with this section, is formed by subtracting the pressure and temperature contribution, each of which significantly exceeds this entropy itself. So therefore the pressure contribution can never be neglected when the temperature and pressure are the main thermodynamic variables. But it's not our case, and we show that it's more precisely in one section. In this case, instead of the simple Boussinesq approximation, it is necessary to use equations that are much more complex for numerical implementation, which are derived in section 5 below, in one section actually. But the next section will be about the energy. I hope that I finished. I don't know how many time I spent. I didn't count, but seems again not so small amount of time. So nevertheless, it's now time for questions. Please raise your question if you have. Yeah. Please check. Yeah, please check. So actually we derive it from this relation. Yeah.
Correct. And next slide, sir. If you go to next slide. 10AB. So here, how the values are computed? These are all two velocities 2 into 10 to the power of minus 3.
Yeah, this value are computed from the real. It's not on the list, but here I put the typical values.
Oh, those values,
which are known, quite well known. I put it there. So I just put this known value to this expression and obtain the corresponding estimation.
Okay.
And this value more or less good known.
Okay.
Of course, with the accuracy, not so high accuracy, but as we reach in this system, but to some extent they are suitable for estimation.
It is adiabatic case. These values are fixed throughout mantle, or these values are constant throughout the mantle, or some particular places. A radius, okay, R is radius, we can take no problem. And but what about the pressure, entropy?
This may be the most important value in this estimation is the relative heat flux. And we just obtain this heat flux by the total heat flux, which is coming out from the score, in terms, of course, that exceed adiabatic value. And then we divide it on the volume of the core. So this is sort of normalized heat flux, which we normalize by the volume of the core.
Okay.
So it's quite relatively well known. And this is this acceleration is going directly from the gravitational acceleration. So it's also quite well known.
Okay.
So, and this is the temperature, which is also more or less known, because the natural experiment with such a temperature, which is everybody believes that it's the temperature typical for the Earth's core, and with the corresponding pressure, there is real experiment. When you hit with a very big speed, one cell with another cell, or make the huge pressure which are inside the Earth, and you can estimate this value. And the most precisely estimated is the density.
Okay.
Because if for this density and this acceleration is most well estimated. There are less well estimated. This one, it's maybe estimated with the accuracy by some 10%, 20%, maybe 30%, something like that. Maybe even 10%. I don't know. Nobody knows exactly. And the most poorly estimated is this one. Because actually it relies on the superadiabatic heat flux, and not from the mantle, but on the boundary from the outer core to the inner core. Yes, and on the maybe which is very deep inside, so it's very difficult to estimate it. In this situation, we even in the worse situation than with Jupiter.
Okay.
In Jupiter, it has quite clear heat flux, and very big one. So we can estimate that almost all superadiabatic heat flux from the Jupiter is going from his surface and almost precisely measurable. So in terms of this, of course, this is very important term, because it actually drives the convection.
Okay.
But in the case of the Earth, unfortunately, we should go up to the inner outer core boundary to estimate this flux, because namely at this position it's most important. Not output, but on this inner core boundary, just because of this gravitational nature of the so of course we should make some proposal. And the general proposal is that this superadiabatic heat flux it's about 1 terawatt. And it's quite well grounded, almost everybody uses.
So these are obtained.
1 terawatt, of course, I mean the total value, not normalized. If you normalize it by this volume, you will get something like that.
Okay. So these are fixed in the adiabatic region of the mantle.
Sorry?
These values are fixed in the adiabatic region of the mantle, right? These values are fixed values. Velocity, entropy, pressure, and the radial. So all the values are fixed in the adiabatic region.
No, it's not fixed value. It's just some average value.
Average, okay.
So it has a many of name. It's you say name it just typical value.
Oh,
You can name it average value.
average.
You can name some intermediate value. Whatever you want.
Okay.
So it's just estimation in order of
Estimation.
magnitude.
Yes.
When you are making the estimation for the magnitude, it's difficult for you to say is it square.
Understood.
Squarely estimated part, but anyhow, it's just the typical part. Maybe the best word is typical part.
Yes. Average.
So we don't know maybe it's average, maybe it's some intermediate value. Because maybe average one is also good word. But then arises the question how you average that. So maybe the best word is characteristic. Just characteristic, another word. Maybe typical, just typical.
Typical values.
Yeah.
It means along the radial direction we have the same values. Along all the radial directions.
Of course, the one thing is necessary to stress that all these values are outside the boundary layer.
Outside the boundary layer.
Yeah, because in boundary layers there is completely another game.
Yes, viscosity changes.
Here we just compare some nonlinear term, not regarding any boundary layer, any shear layer. We are not considering that.
Okay.
We are, all the stuff which we considered here is in the bulk volume.
Okay, thank you.
So for the mantle convection, so how we have to
For the mantle convection.
these equations.
For the mantle convection, it's quite another situation. Because in mantle, the viscosity is so huge. In the major problem for the convection, maybe problem, or maybe another word, lack of the convection in the our core, outer liquid core, that is viscosity is tremendously small. Actually, this Ekman number is a measure of the viscosity. And this Ekman number is so small that we, from one point of view, we have a difficulty to explore it numerically. But it's the heaven for the asymptotic people. Because they see that they can investigate it asymptotically, approximately, and so on, and to make make use of the boundary condition and match everything. But in the mantle inverse situation, it's have so huge viscosity. So then in mantle, if the main advance, maybe I already told, but the main advance of the small Rossby number which work in this situation is that we, in fact, effectively remove nonlinear term here. But in mantle, because of big viscosity, this nonlinear term become quite important. And it raises a lot of difficulty. And another difficulty in mantle is that actually we even know, we even don't know for sure how this material is constructed, which is inside the mantle. Because on some scale, which is lower than some hundreds of thousands years, it can be regarded as rigid stuff. But on the larger time scale, up to the million years and maybe more, maybe slightly less than million years, it can be regarded like a liquid. And not simple liquid, because it has some fraction of the heavy metal. So actually, if we say the truth, there is no any proper theory for the mantle convection. Most of them are quite speculative. But there is proper theory for the convection in the Earth's liquid form, and very proper theory, very accurate, and which prognose the results very accurately and very good. But there is no even a trace of such a theory in the mantle.
But people are working in mantle convection.
Yeah.
Yes. Yeah. Okay.
Yeah.
The depth of the outer layer,
Sorry?
that R star,
Yeah.
this is depth of the outer layer, outer core.
No. You got it completely wrong. This star notation, this index star, means that this is a typical value. It's not. It's just a typical value. And here I just stress, if we consider in this context R star,
Yes.
as you're talking about, this is actually typical derivatives. So you take in the derivatives, then you get the values. For example, you take V, divided it by the derivatives of V in R direction. So effectively you get R. And this ratio, in fact, is the typical value we are looking for some typical derivatives, for some typical velocity. So this is, and other name for this value is, as we already discussed, is typical value, characteristic value, medium value, whatever you saw. But it's necessary especially to stress that this R star is quite different from the RO, RI, which we use to measure the radius of the inner boundary, outer boundary. And it's indeed sufficiently low. You see that here from this estimation we have almost 100 times lower value than for the outer core.
Yes.
So it is the radial direction. R stands for the radial direction, right?
Maybe it's wrong position to mark it IR, because then you can mistake it with the radial direction and so on. Maybe more correct was to mark it as L, maybe, because people start to wrongly understand it and mix with the R, which is, it's not necessary in the R direction, of course. It could be in any direction.
Because in fluid dynamics, R means position vector we take, no?
Yeah.
In fluid dynamics, R means position vector or radial direction. This type of wordings are there.
Sorry, this is actually perhaps the big mistake of this representation.
Yeah.
Better instead of this R star to have maybe L star.
Something. Abbreviation.
Something,
Abbreviation.
Because if you write it as a small r, so everybody thinks that it is the radius. but it's not the case, of course.
Fluid dynamics language, symbol R means radius.
Yeah.
Fluid dynamics, MHD, etc.
Since you catch all our mistakes, we correct them. Thank you for catching.
Okay. Thanks, Professor, for the depth analysis of this accuracy verification by nonlinear scaling. Okay. So today morning we had the lectures. So today we finish this one. In the afternoon we will have the presentations. By 2:30 we will start. Okay. So you can relax for some time.
Okay, thank you.
Okay.
I didn't count the time. How many time I spent? I didn't count.
Chair you can. Chair you can. Now I request our mathematics department HOD, Professor R.S. Selvaraj sir, to come forward to felicitate our speaker of the Gian course, Professor Rameshwar from Osmania University. Please, sir. Because sir will not be available on Friday for valedictory. So I invite. Yes, sir.
Hello, sir.
Well, glad to see you.
How are you?
I'm okay, more or less.
Yeah.
More or less.
General function, I was not here. I was out of
Okay. Mm. Okay. Thank you for coming. Very great pleasure. I don't know. Should I remove that from me? Or-
Yeah, you can do practice it, yes.
Or maybe I should pass it to somebody.
No need, no need. Yes, sir, please. Come to us. One chair is.
You are not going to be here for a while.
Yeah.
Yeah.
Because
Photographer is confused.
No, we cannot believe it. Okay, yeah. Photo it. Yes, sir, please. Sir, Maria, madam. Maria, please come. Professor, please come.
I have chosen this topic. Besides being a chemical engineering background, everything is surrounded by, according to me, fluids, more or less. And more importantly, the science behind it is basically maths and physics. So if we are good in maths and physics, we can solve almost all kinds of problems, almost real as well as practical. That is why I have decided to work in this field of domain. And since I'm beginning to work, let's see how far I can go. That is my aim. And today I'm going to present on the topic of initial equation of geostrophic flows. So here I'll explain first the basic equations that is taken into consideration in geostrophic flow and some of the characteristic values as well as some parameters. So can I get the portable mic?
This one or okay.
Okay. Hello. Okay, so I'm going to start. So the whole topic of this workshop was based on planetary motion. And for that we have to know one common or the basic force or effect, that is the Coriolis force. The Coriolis force is associated with objects that are in rotating motion. So suppose let us take the example of our Earth. Earth is a spherical geometry or geoid. It rotates from west to east. The motion of the earth is from west to east. And whenever an object, suppose there is an object or here is an object in the northern hemisphere or in the southern hemisphere, whenever an object moves from, suppose from pole towards the equator, then it experiences a force due to the rotating motion of the earth. And that force is called the Coriolis force or Coriolis effect. Any object experiences that force while coming from the poles to the equator side. So here, the problems that we face in geostrophic flows, they are governed mainly by some equations, initial equations, which you can call as a continuity equation. Then if the viscous effect comes into force, then we use the Navier-Stokes equation. So I'm going to start with the Navier-Stokes equation. I'm basically going to write the equation. This is the representation of the Navier-Stokes equation. This first term is an unsteady term because here the velocity is changing with respect to t, that is time. And the second term is the convective term, where basically it defines that the transport of momentum is happening due to the motion of the fluid. And this third term has come into this equation because of the Coriolis effect. It is 2 omega into del v with a vector v, velocity. And also this omega represents the angular velocity because of the rotations that it has. And the fourth term is the viscous term. And then here this is the nu, then gradient square into v vector. Then last term is the pressure term, gradient of pressure. So the pressure term implies that there is some pressure force acting on it, and it's in the negative sign because we know that pressure tends to flow from higher pressure area to region to a lower pressure region. That is why the basic representation of this equation is in this form. And next, let us draw a figure of our Earth, the interior of the Earth. This is the Earth's radius, outer radius. Its interior has, we know, crust, mantle and core. this part is the mantle and the inner part is the core. But from geography, we know that the core is comprising of two phases, that is one solid and a liquid. So this inner part is the solid one and this bigger part is the liquid one. Though the whole core, since the earth is a solid structure, we tend to understand that the interior of the earth is also solid, but that is not the case. Inside we have a liquid phase which comprises along with the solid phase makes up the core of the earth. So the radius, the tentative or approximate radiuses are given. The inner core radius is 1222 in kilometer, and then this CMB, that is core mantle radius, is the approximately 3480 kilometer, and Earth's radius can be written approximately as 6366 kilometer. So this is the basic interior of the Earth with different radiuses of from like crust, core to mantle. So if we take into consideration two characteristic values, that will be the size and the velocity. So for size and velocity, we can use this sign notation as V star, and for size, which can be also called as characteristic length scale, you can write it as R star. If we consider the inner radius, that is Ri for the inner radius, smaller radius, 1222 kilometer. And now from here, if we want to calculate the time scale that is required for this whole rotation, we can write it as T star equal to R star by velocity star. If we calculate it, we will get precisely as 1.2 into 10 to the power 10 seconds. So this is basically some characteristics. There are many other characteristics, but I have taken just the velocity and the time part. Now, coming to the parameters in geostrophic flows, there are basically two parameters. Or dominating the system of the rotation of the fluid. But if it is more, then it will imply the condition that the inertial forces are more into effect. So in geostrophic flows, we need to have this number very, very less. Then only the geostrophic flow equation, this parameter will come into effect. Then there is another parameter. Okay, first I can its formula is given as V star by omega small r star, where V is the velocity and omega is the rotation for the earth. Suppose if you consider earth, then r is the characteristic length. If we need to find some value of Rossby number, we can take all these values into consideration and find the value of r. The next parameter is the Ekman number. Ekman number is the ratio of viscous force to Coriolis effect. Here also, if the Ekman number is denoted as capital E, if it is very much less than 1, then it will imply that in the system of rotation, the Coriolis force is dominating the viscous force. So we have seen, I have learned from here that E values is, for geostrophic flow, it is seen as very, very less than 1. That implies that the rotational effect is dominating the whole system of the fluid or object that we are taking into consideration. So these two parameters I have come to learn about geostrophic flow. Since this topic is very much new to me, that is why I applied for this course, and I came to know about many more things, but there is still some things left to understand, which I'm sure I will learn over time. But thank you, sir, for explaining us in such a simple way, and I hope my presentation justifies the small topic that I have chosen. So that's it. If any questions, then I'll be very much happy to answer.
Thank you. You give a very interesting presentation, but the point is that you name it as geostrophic flow.
Geostrophic.
Yeah, but what is the condition of the existence of geostrophic flow? Which parameter should be equal to what to get the geostrophic flow?
So as per
Actually, you have two parameters. One is
Rossby number,
and the second.
Ekman number.
So to get geostrophic flow, what should happen with these two parameters?
The Coriolis effect comes into
No, just the number. What they should be equal to get the geostrophic flow. Just
yeah, this should be very much less. So it can be zero. It should be zero.
yeah, actually, yeah,
Very much,
you're
negligible.
right. Because namely at this condition, when both are zero,
Yes.
so we getting geostrophic flow. And maybe you didn't spoke about that, but what is the main feature of the geostrophic flow? What kind of dependence is there?
Differential rotational flows.
Yes, but it's depend only. Did it depend on two or three coordinate, or just on one?
Viscous flows
Coordinate system.
in coordinate system.
Yeah.
Spherical
So
coordinate
what is the major coordinate for the geostrophic flow? With which it change?
cylindrical coordinate
Yeah,
system,
yeah,
three
exactly.
direction.
Cylindrical radius,
Yes.
actually. This is almost only what affects the geostrophic flow. Okay, thanks.
One more thing. You have written the equation there, isn't it? Can you put it in the non-dimensional form such that this Rossby number and Ekman number appear there?
A non-dimensional form.
Where they will come into picture in the equation?
You just put this number.
Write down there. Ekman number.
No.
It's Rossby number.
The 10 was the number. Yeah, divided by.
Yes. Then Ekman number.
I think this plus force.
Okay. Now, what you said for the geostrophic flow, what is the condition?
That
Almost zero.
this should be zero. Then only it will come into effect.
And so, what is happening there? Which are the terms going away?
This, this, and this.
So, what you left with there?
Then left to it only this Coriolis term and the pressure gradient. These two are mainly important.
Yeah. So, you have to solve that.
Yes.
Okay. Okay then. Yeah.
Thank you, ma'am.
Good.
वो वाला हटा ही दो.
Okay. Good afternoon to everyone. My name is Mogila Junavin. I am from Equi Foundation for Higher Education, Hyderabad. I am under the supervision of Dr. Gautam Kumar, and my area of research is fluid flow or porous media. And today I am going to discuss about the task number 2.4.2, which was given by Professor Starchenko, sir. As of now, Kangana was derived the momentum equation to the planetary convection, planetary motion. Now the task is task number 2.4.2. is that carry out the detailed transformations to obtain the system of three scalar equations 2.9 from the first equation, from the first vector equation of the geostrophic system 2.8, where 2.8 is given by two v cross del z minus del p is equal to 0, where this del g is the unit vector in z direction, and this is the pressure gradient, and this is the vector, and this whole term represents the Coriolis force, and this term represents the gradient of the pressure. And we have to show that 2.9, which is given by del p by del z equal to 0, and v phi is equal to 1 by 2 del p by del s, and vs equal to minus 1 by 2s del p by del phi. Okay, to prove this 2.9, we are going to use the cylindrical coordinate systems to the geostrophic momentum equation. So we convert from x, y, z to s, phi, z, where s is the radial system, radial component, p is the azimuthal component, z is the vertical component. So the vector v is given by, from in cylindrical coordinate, vs, v phi, vz, and the gradient p is given by del p by del s, comma 1 by s del p by del phi, comma del p by del z. Okay, let's rewrite this system 2.8. 2v cross del z equal to del p, and where this vector del z is 0, 1, not vector, this is the unit vector. Okay, so let's calculate this 2v cross del z. Which is given by, okay, del s, del phi, del z, and v is the vs, v phi, vz, where del z is the 0, 0, 1, where del s, del phi, del z are the unit vectors in cylindrical coordinate system. Let's calculate del s times v phi minus del phi times, okay, vs plus del z times 0. So we are remaining with v phi. Okay, this is 2 multiplied by 2 v phi, 2 vs minus 2 vs, comma 0, So let's compare this equation 2.8 with this del P and 2V cross del Z. We'll get del P by del S is equal to 2V5. From here we'll get V5 is equal to 1 by 2 del P by del S. Similarly, 1 by S del phi by del S is equal to minus 2S. From here we will get Vs equal to minus 1 by 2S del phi by del S, and another one is del P by del Z is equal to 0. And these are the required system you have to show. Okay, and thank you. Cylindrical coordinate system, sir, we are viewed. Z, sir. Z is independent. Remaining are dependent. S is dependent on S and phi. Yeah. Yeah, sir. Radial and azimuthal are dependent. Thank you, sir.
Good evening, all of not going. Good afternoon. Myself is Kamlesh Sej. I'm from Chennai. My institute is SRM IST in Katagulam campus. My research topic is FSI and in blood flow in using the arterial. My area is fluid dynamics. I taking the today topics finite volume methods. So I go for 2-dimension study diffuse equations for discretization. Two and 2-dimension dou by dou x of lambda dou phi by dou x plus dou by dou y lambda dou phi dou phi by dou y plus source term equal to 0. Now first and take a grip point and knobs. This center point is P, and this east directions and west directions. Y directions are north direction and south directions. N2 E is the direction is we taken del x del y n, E to S del y s, and these total directions del y. West to S is del x w, south to east del x e, and these total directions del x. And first equation we integrated in over the control volume, integrated del v dou by dou x lambda dou phi by dou x del x del y plus integration over the del v dou by dou y lambda dou phi by dou y del x del y plus integrations s phi del x and del y equal to 0. Now integrate that and we get finally lambda e lambda dou phi by dou x into del y from E minus del to dou phi by del x from del y from w plus lambda dou phi by dou y del x from north minus phi dou phi by dou y del x from south, and we write source term as capital phi into del v equal to 0, and we substitute in the limits and we write the flux phase terms dou phi by dou x to E, we write phi E minus phi p divided by del x E phi dou phi by dou x from W, we write phi p minus phi E phi W dou x W dou phi by dou y n phi n minus phi p del y n dou phi by dou y 2s phi p minus phi s divided by del ys, and we substitute the third equations. And also the substitute the lambda e a by del x e phi e minus phi p minus lambda e aw del x e del x w phi p minus phi w lambda n a n by del y n phi n minus phi p plus lambda s as del ys phi p minus phi s, and we source term write the for linear model sc plus sp phi p. Now all term we rearrange the phi p ae plus aw an as I give the value for ae equal to lambda e ae del x e aw equal to lambda w aw del x w and an equal to a lambda n an del okay ma as equal to lambda s as del ys and ap right ae ae plus aw an and as and source term sp del x and del y, and we rearrange ap phi p equal to ae phi e plus aw phi w plus an phi n as phi s plus so and this is get the result for description 2 dimensions over. Yes. Ma'am, here using the Gauss divergence theorem to volume to surface, and then we integrate the normal wave for to surface. The divergence theorem requirement to the volume convert the volume to surface area, surface integrated.
Could you estimate somehow the accuracy of your scheme?
Scheme,
What is the accuracy of this scheme? Can you estimate it somehow? Or error, otherwise error. Can you estimate the error via this some, I don't know, deltas or whatever? Second order, yeah? So in terms of this delta, yeah?
Second order.
Second order.
Okay. So you have to work for the boundary nodes also.
Yes, ma'am.
Okay. You know na boundary nodes.
Yes, ma'am.
Yeah, near the boundary it is half of the grid size.
So after the unit side, the del x by 2, ma'am.
Del x by 2 also will come. Del y by 2 also will come. Because you have dealt with the two-dimensional case. Yeah. So, okay. That also you have to write down separately. This is for the internal nodes.
Internal also.
Okay. Have you tried any problem?
No, ma'am. Now only started this topic also, finite volume method.
Where you want to use it? For your
in my research, ma'am.
In your research work. Oh, very good. So you understood.
Yes, ma'am.
Good. Okay. Good.
Thank you, ma'am.
Yeah, good afternoon, everyone. My name is Anup Suresh. I'm from Bangalore. I'm doing my PhD in Vellore Institute of Technology in Vellore. And the topic of my research problem in PhD is the study of the investigation of chaos in nonlinear dynamical systems, particularly in magnetoconvection and rotating convective systems. So the topic I've chosen for my presentation is Introduction to Weakly Nonlinear Analysis through Regular Perturbation Methods. So firstly, let me comment on what we mean by weakly nonlinear. So basically, when we say weakly nonlinear, we're referring to a small nonlinearity that arises in equations. So basically, terms with or equations with nonlinear terms which are small in magnitude. So so when we have such equations, we can treat the nonlinearity as a perturbation to the linearized problem, as in we can treat the nonlinearity as a correction to the linearized solution to the problem. And doing so allows us to pursue different sorts of perturbation techniques for us to solve the problem. So in general, any kind of weakly nonlinear system can be expressed as a general form as Lu plus epsilon n of u equal to 0, where epsilon is a very small parameter. Yeah, so this is the general form of a weakly nonlinear problem. Lu here is the linearized problem. So Lu equal to 0 gives the linearized problem, where L here is the is any kind of operator, a linear operator. U is a dependent variable. Epsilon is the perturbation parameter, and n of u is the nonlinear term in U. So basically any kind of nonlinear term in U. So here the condition for us to use a perturbative expansion is when epsilon is very much less than 1. That is, epsilon is a very small parameter. So for such a system, or such an equation, the general solution can be expressed as U equals U0 plus epsilon U1 plus epsilon square U2 and so on. So basically the solution can be expressed as a series, a perturbative series, and this is only for what we call as regular perturbation. So again, there are two types of perturbation. Coming to the types of perturbation, we have regular perturbation, techniques, and we have what are known as singular perturbation techniques. So now what are the main differences between regular perturbation techniques and singular perturbation techniques? Now in regular perturbation techniques, the solution here, so this is the solution, varies smoothly with epsilon, where epsilon is a perturbation parameter. Examples, I'll just write it here. R stands for regular and S stands for singular. So yeah, so example for a regular perturbation problem, let's say x minus epsilon x square equal to 1. So epsilon here is the perturbation parameter. For singular, it's epsilon, let's say y double dash plus y prime plus y equal to 0. Now if you can see here in singular perturbation problem, epsilon occurs as a coefficient of the second order of y, differential coefficient of y. So so in such a problem, in such a singular perturbation problem, so the solution exhibits a rapid variation in some regions, some domains of epsilon, and does not vary smoothly with epsilon. In contrast, regular perturbation techniques, the solution has to vary smoothly with epsilon. And which comes to my second point, which is that in regular perturbation techniques, as epsilon reduces to 0, that is, as epsilon tends to 0, we arrive at the linear case. So in this case, when epsilon is equal to 0, we get u equals u naught, which is the solution to the linearized problem LU equals 0. And you can just see here, when epsilon equal to 0, we get x equals 1, which is the linear solution. And the perturbation when epsilon is small is about the linear. So epsilon something plus epsilon square something and so on. Whereas you don't have that case in the case of nonlinear, I mean, a singular perturbation technique, because when you equate epsilon equal to 0, what you arrive is not the second order differential equation, but the first order differential equation, which is different. The nature of the solution itself is different when you compare to the second order. So in regular perturbation techniques, the solution converges uniformly to the linear solution when epsilon tends to 0, whereas in a singular perturbation problem, it may or may not converge uniformly to linear solution as epsilon tends to 0. And so in regular perturbation problem, the solution can be expressed as a Taylor series, as in any sort of series, whether it's Taylor or Maclaurin. Whereas in singular perturbation problem, it cannot be expressed in the form of Taylor series, at least not in all domains of the problem. So those are the differences between regular and singular. So now coming to my main topic, which is basically here we are only dealing with regular, because in singular it's still a hot topic of research and not very many things are known about singular perturbation techniques. Whereas regular, we know quite well about regular perturbation techniques. So let me give a simple example to begin with. So we take the same example, x minus epsilon x square equal to 1. I'll rewrite this in a familiar form, which is x minus 1 equals epsilon square. So as you can see, this is linear, whereas non-linear term occurs in the right hand side. And setting epsilon equal to 0, as I said, gives you x is equal to 1, which is the solution to the linear problem. So let's express the solution for the non-linear case, for the equation, in terms of series expansion. So I take x naught plus epsilon x1 plus epsilon square x2 and so on. So we already know that x naught equals 1, but we'll show that we obtained the linear case at the first order of epsilon. And to do this, we just substitute the expansion in the main equation. So we have x naught plus epsilon x1 epsilon square x2 and so on, minus epsilon x square now. So I take the same equation, and I've rewritten it, so it's like, so now now we rearrange in such a way that we obtain different orders of magnitudes for epsilon. And so we have just comparing, we have x naught plus epsilon x1 plus epsilon square x2 and so on, minus 1 equals epsilon. We have let me just consider the first two terms and neglect the others. So we have x naught square, a plus b the whole square is epsilon square, plus x naught square plus epsilon square x1 square. Then we have plus 2 x naught 2 epsilon x naught x1, and this goes on. So now I gather the terms which are coefficients of epsilon at each order, and what I get is at the first order, that is at epsilon to the power of 0, the leading, what we call as the leading order, we get this. So this is nothing but at the first order. So that is, what I get is I get x naught minus 1 equals, there's no term of the leading order here, so 0. Which is basically what we get as a solution to the linearized problem. So that this is basically what it means is we're just setting epsilon equal to 0. And what we get is the linear problem. Now, so this is basically the trivial case. Now, gathering the terms at the first order of epsilon, we get, so we have this term here, epsilon x1, so x1, and we have epsilon x naught square, so it's x naught square. So we already know the value of x naught, which is 1. So at the value of x1 is 1 again. Now we look for terms which are at the second order of epsilon, and so
Anup?
here we have epsilon x2.
Anup, just your battery is low. You want to change it.
Yeah. So gathering the terms at the second order of epsilon, we get x2 here. So equals epsilon x naught square, which is yeah. So yeah, this term here, epsilon times epsilon, so you have 2 x naught x1. So we know the values of x naught and x1. X naught is 1 and x1 is 1, so we get x2 equals 2. And similarly, for epsilon cube, we have x3, which is here. X3 equals, we have x1 square plus yeah 2 x naught x2. So here there's an additional term here, so it's 2, we have 2 x naught x2. So that is, so x3 is, x1 is 1 plus 2, x naught is 1 and x2 is 2. So 5, right? So, and so this we can go on epsilon to the power of 4, 5 and so on, but we just since we've obtained 4 terms, we're in a position to write the series. So the solution is x naught is 1 and epsilon x1 is again 1 x2 is 2. So we have 2 epsilon square plus x3 is 5. So 5 epsilon cube and so on. So basically epsilon, this term here is the correction to the leading order. 2 epsilon square is the correction to the first order and so on. So we managed to obtain a solution as a series expansion in epsilon for the value of x. And again, just checking, epsilon equals 0 reduces our problem to the solution of the linearized case, which is x equals 1. So yeah, this is a simple problem, simple algebraic problem. Next, let's study the case of a little more complicated problem, which is a differential equation. And one such differential equation involving regular perturbation scheme is what is known as van der Pol oscillator. And van der Pol oscillator is an example of an oscillator which is non-conservative and has a damping term of the first order. So we have so the equation of the van der Pol oscillator is given by d square u by dt square plus u equals epsilon 1 minus u square du by dt, where epsilon is a very small parameter. Now if you can see, d square u by dt square plus u equal to 0 is the equation of a simple harmonic oscillator, or just a harmonic oscillator. And this term here is the damping term of the first order, which has du by dt, and so it's a damping term. And so such an oscillator is non-conservative, as in it doesn't have a periodic solution. So we have performing similar sort of analysis. We can just obtain the linear case, which is when epsilon equal to 0, we get the usual harmonic oscillator equation, a periodic harmonic oscillator equation, and the solution to such an equation is given by u equals a cos t and phi. So you all know how the solution can be obtained. You have a differential equation of the second order, which is homogeneous, and so there's only complementary function. They're solving this, we get this equation. In general, it can be expressed as both sine and cos, but this phase shift or like phase angle makes up for the sine as well. So we have a cos of t plus phi as a solution. Now, so again, the solution of the original equation, that is a nonlinear equation, can be expressed as a function of t and phi given by u naught of t, which is basically this this term, the linear term, the solution to the linear problem, plus epsilon u1 plus epsilon square u2 and so on. So yeah, let me just call this 1, 2. So now we substitute equation 2, which is a series expansion, in the original equation 1. So we substitute 2 in 1 to get So we get so I'm just substituting and rearranging. So d square u1 by dt square plus u1 plus the coefficient of epsilon square, which is d square u2 by dt square plus u2 and so on. And then we have the right hand side, which is epsilon 1 minus u0 plus u1 plus u square, 1 minus u square. So we have the square here, and then we have the first order differential, which is u1 by ut plus epsilon square du by dt and so on. So now rearranging the terms, we get d square u0 by dt square equals u0 plus epsilon plus
Anup, you have taken 15 minutes.
yeah.
Yeah. Write the answers now if possible.
I was not
Proceed.
informed that 15 minutes is the limit.
No, no.
If you do the substitution, what you get at epsilon naught, you get the same equation to the linearized problem, which is u naught equals a cos of t plus phi, right? And at the first order, so what we get is d square u1 by dt square plus u1 equals 1 minus u naught square du naught by dt, and we just substitute the terms. We already know the formula for u naught, which we obtained in the first order, and so it's basically a trigonometric function. So performing, trigonometric manipulations, what you get is just write it here. This is the answer for the first order. So you have u1 equals, we have a cube minus 4a by 4 sine t plus 5 plus by 1 by 4 a cube sine t plus 5 after performing trigonometric identities. And so now we can obtain the solution for u1. You can treat this as a complementary function, and you have the particular integral, the part given by this, and then we obtain the solution u1, which is I just write the particular solution. General solution just follows from that. So which is minus a cube by 4a by 8 t cos t plus 5 minus 1 by 32 a cube sine 3t plus 5. So this is for the particular solution. And so now from this you can obtain the formula solution for u1, and now you have u0 and u1. You can do the second order as well, but I'll just stop at the first order, which is to get the general solution as u1 cos of t plus 5, which is the linear solution. Sorry, u equals the solution, and then you have epsilon u1, which is given by this, and if you want, you can carry take it to the further orders as well, u epsilon square u2 and so on. So this is how you solve a regular perturbation problem when it comes to a differential equation such as van der Pol oscillator. Thank you.
Thank you for interesting topic. We just mentioned that this is very much resumes that Rameshwar did in his lecture.
Yeah.
So perhaps we are working together, is it?
No, we're not working together. Yeah, I just chose this topic.
Okay, so one small question is that is this dependence with taking into account first to the correction, is it still periodical or?
No, this is not periodic because it has t here. This is periodic because it has a cube sine 3t plus 5, whereas because of this term, it's not periodic. And which is why it's called as aperiodic oscillator. Van der Pol oscillator is an example of a non-periodic oscillator.
But this addition, is this some sort of the trend, or what is that actually?
As in?
Is it some sort of the trend, or maybe it's what form this addition have?
I mean, so basically when we...
So on top of periodic solution, is anything that just trending it away from the, or maybe it tends to infinity, I don't know.
Yes. So you consider more and more of these terms, you gather more and more of these terms, you start making the solution more and more non-periodic. As in non-periodicity occurs in each of these terms. And the original at the first order, at the leading order, it is periodic. This is basically when you substitute epsilon equal to 0, you obtain the regular harmonic oscillator, which is a periodic oscillator. But as in when you gather these terms here, epsilon u1, epsilon square u2, so u3, u4, u4, the solution starts becoming more and more non-periodic.
But all this correction, especially the more higher corrections, they are multiplied by a small parameter. Maybe this non-periodicity somehow compensates each other. I don't know.
No, because compared to this is a small parameter for sure. But even this depends on the value of epsilon that you're taking. The overall solution is non-periodic. So when you plot the graph of a Van der Pol oscillator, what you can see is a damping term. And if you look at this equation here, when epsilon is not equal to 0, even when it is a very small term, this may not necessarily be a very small term. For instance, the general form of a Van der Pol oscillator doesn't mandatorily require epsilon to be a very small term. We have taken it to be a small term for us to solve it using perturbation analysis. In general, epsilon can be 5, 6.
But is there any physical justification of smallness of epsilon or not?
I mean, when it is small when the damping is small. So when you have a small you have a harmonic oscillator and you have a very small drag coefficient is very small. Let's say air resistance, which is very small, which is, resistance nonetheless. So because of the drag force, it includes a very small parameter, small non-linearity or non-oscillatory characteristic to the system. So when the drag force is large, epsilon, which means that epsilon is large, you have a totally different solution which we cannot solve using nonlinear analysis because this term becomes very large.
Oh, okay.
So this is applicable only when epsilon is small, and so we have taken. So this is basically as I said, this doesn't require for the general Van der Pol oscillator. This doesn't require a very small term. It may be a very large term as well, but for us to solve using nonlinear analysis and perturbative methods, this has to be small. Only then we can solve using regular perturbation techniques.
Okay, thank you. But maybe my final question is much more severe. You started from the algebraic equation, yeah? And in this algebraic equation, you put the regular perturbation and found that it's working.
Yes.
But if you look better on this equation, you see it's just quadratic equation. And it has second solution, which is inversely dependent on epsilon. So so your regular system becomes singular.
Right. So no, that was just so you mean this x minus epsilon, this one?
Yeah, exactly. Yeah. It's actually a quadratic equation, and if we consider the second solution of it, you consider only one which is close to 1. But there is a second solution.
Yes.
An order of magnitude of this second solution is roughly proportional to inversely proportional to the
Yes, yes,
square from epsilon. So,
Yes, yeah,
so it
so-
becomes singular.
Yes, yes. This.
So this is sort of interesting problem.
Right. So through I just considered this problem to show the method of regular perturbation. So
Yeah.
in general, of course, we don't solve these kind of problems in regular perturbation method. This is just for me to as an introduction to solve the van der Pol oscillator equation.
Okay.
So we don't generally solve such equations in using regular perturbation techniques.
Okay. Thanks.
So this was just an example, like a prelude for me to.
But nevertheless, this is an interesting problem.
Yes, yes.
Which start to be regular, then it's become
Yeah.
singular.
Okay, I want to know, is there any restrictions on this method? When we have to apply, when we should not use this one?
Yeah, so when it comes to van der Pol oscillator alone, as I said, this is applicable, this sort of regular perturbation scheme is applicable only when the coefficient is very small.
Ah,
So let's say the coefficient is you have d square u by dt square plus u equals, let's say this is you have a simple harmonic oscillator equation. And with in physical problems, you have a very small drag coefficient. Let's say in fluids or even for that matter, air resistance, which is 0.001 or even smaller. And then you have the damping term given by this. And since epsilon here, we can take this to be epsilon, which is a very small parameter, and then we can apply our nonlinear analysis. But if this is very small, even if this is like 0.9 or close to 1, even if it is less than 1, it takes a lot of terms for it to converge. So practically speaking, we won't be able to apply. Even if it is not greater than 1, but less than 1, but still, of the order of, greater than 0.5, 0.6, this sort of method is not practically applicable. So.
okay, good. Yeah, nice presentation. Yeah, thank you. I hope all of you have submitted the assignments. Yeah. Okay then. So tomorrow we meet again and 2 more days to go. Isn't it? Tomorrow Thursday, Friday. Friday 4 p.m. we will have the validation. Okay. Okay then. Thank you.